跟你说吧，所以所以就是我。对，味道也我真觉得。一个人说出来，今天你从那个玻璃出去，还是我付你说的？你付啥付？我给他拼了。啥？我站你，肯定站你的，他不懂什么。直接把他销售死。这他做不到。这他做不到，为什么？
Guys, can you do question 4, please? Because this will be the question. Can you do question 4, 5, 6, and 7? 4, 5, 6, and 7, guys. Got this one.
这话是谁？
Can you do question 4, guys, please? Just do question 4, sir. Question 4. Question 4. You guys do question 4, please. You got it? Okay, thank you. Thanks a lot, sir. Alright guys, have you already done question 4 guys yet? Alright guys, so you have x1. Can you guys listen? If you haven't done question 4, can you listen guys please? You have a random sample from a normal distribution with these parameters. Now you remember what I taught you some time ago, that if you have a random sample from a normal distribution, then the MLE for the mean is the sample mean, right? In this case, so the MLE for alpha plus beta is equal to x bar. Do you guys follow this or not? Yeah, because I taught you this while ago that when you have a data set from a normal distribution, the MLE for the mean parameter is the sample mean, right? So the mean parameter here is alpha plus beta, so the MLE for that is x bar, so which implies that the MLE for alpha plus the MLE for beta is equal to x bar. And similarly, you have the second sample, this IID with normal with these parameters, right? So once again, by the same argument, the MLE for alpha minus beta is equal to y bar, right? In other words, the MLE for alpha minus the MLE for beta is equal to y bar, right? Call this equation 1, call this equation 2. Now we have 2 equations and 2 unknowns, right? Unknowns are alpha hat and beta hat. The equations are 1 and 2. Now if you add the 2 equations, 1 plus 2, you get 2 alpha hat equal to x bar plus y bar. Alright, so alpha hat is equal to x bar plus y bar divided by 2. Now if you subtract equation 2 from equation 1, then you get 2 beta hat equal to x bar minus y bar. So beta hat is equal to x bar minus y bar divided by 2. Alright? So you're done guys. It's easy, right? So this is the estimator for beta, ML estimator for beta, and this is the ML estimator for alpha. Yes, guys? Any questions, guys? Or anything not clear, guys? I'm sure many of you have already done this. You guys okay? Yeah, you can do it this way too, yeah. But this is the wrong way. You can do it this way too. But it's not more complicated. You could do the same answer, yeah. Yeah. I'm glad that you started like that because that's the wrong way. Yeah.
Statistician.
Are you guys okay? And you do the next question, guys. Question 5. You want to say? Let me show you. The question number 5 is on the gamma distribution, which is the PDF for the gamma is on page 8. Page 8 of the lesson notes. You have the notes with you. You guys have the notes now? Yes. Yeah, you can do it like that. We have to do it like this, yeah. Yeah, you can do that. Yeah, but you get the same answer. Yeah, you get the same answer. Yeah. Guys, the density for the gamma distribution is on page 8 of the lecture notes. If you want to know about it. Towards the bottom of page 8, so what are you looking at? Yeah, you got it, yeah. It's equation 35. Yeah.
This is just a, no, it's a tau, yeah. So tau is a function of lambda. So once you find the MLE for lambda, the MLE for tau will be just 2 lambda hat minus 1 square. So you just replace lambda by lambda hat. Yeah, yeah. Yeah, I know. It's just kind of it's known as the invariance property. It's in the lecture notes, but I didn't talk about it. But it's known as you have a one-to-one function of an MLE. Then if theta hat is an MLE of theta, then g of theta hat is also an MLE of g of theta. But g is a one-to-one function. Yeah, in this case it does work, but it doesn't always work. You're right, yes. It doesn't always work. Yeah, I mean, the normal way to do this question is to write down the full likelihood and do the partial derivatives and set them to 0. Yeah. And you will get the same answer though. You get the same answer. Yeah. Yeah. Yes, but this is the only one. Yeah, I know. I think the best way to check if it works is to actually do it the normal way and see if you get the same answer. Like in the exam, I wouldn't know. Yeah, you can kind of like use for this course, yeah. Alright, then you guys start question 5, guys. All right, you have a random sample x1 to so you have a random sample from a gamma distribution with these parameters, but then we are assuming that the parameter r is known. So the only parameter that is not known is the parameter lambda. So basically you have only a one parameter problem. Okay? You just have so you just have one parameter problem, right? So the first thing to do is to write down the likelihood for lambda, because lambda is the only parameter. Yeah? So that would be that would be the product of the density function, which I'm trying to see here is lambda power r all right. So this is the likelihood function, right? And take the product, guys. You get
This is what you get. You should take the product of the density functions. Next step is, I'm sure you've done this enough times, hundreds of times, guys. So you should be bored by now doing this, guys. So taking the log likelihood, guys, this is what you will get. Alright, and the next step is to take the derivative with respect to lambda. That's the only parameter. So you get this, and you set this to 0 and solve for lambda. So lambda hat, say, is nr divided by the sum of xi, and this is basically r divided by x bar. Okay, now to make sure, because this is a one parameter case, you need to make sure that this is an MLE, right? To do that, you know what to do, guys. You just do the second order derivative, which is minus nr, and which is of course negative all the time, right? And hence lambda hat equal to this is an MLE. Now the question also asking you to find the MLE of this, guys. Now what you need to find the MLE of this, all you have to realize that this is a function of lambda. So by one of the properties of MLEs, to find the MLE of tau, all you have to do is just replace lambda by lambda hat. Alright, so the MLE of tau, this is tau, okay, is simply 2 lambda hat minus 1 squared. So this will be 2 r. This is known as the invariance property, which is in the lecture notes on page 16 or something, right? So to find the MLE of this, you just replace lambda by lambda hat, and that's what you get. Okay. All right, guys. Any questions, guys? And you do the next one, guys. Question 6. If this is okay. Yes, all of you guys sign the attendance sheet. Yes. You can use this property yet in this stuff. Yeah. You could do this question like this too, yeah, and you will get the same answer. Yeah. Yeah. I know, sorry, but in the lecture today I use N and N.
Yeah, I know. But if it is M and N, then the answer will be slightly different. Yeah, it will be slightly different. Yeah. 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 Oh. Yeah. You can use the moment generating function approach. Try to find the MGF of this and show that it doesn't go to the MGF of the normal distribution. Yeah, that's one way to do it. Yeah. You guys okay? Yeah, you're right. Yeah, A and K must be positive to have this picture. Yeah, I should have mentioned that. If you guess it, go on. Oh, yeah. Okay. It's not how I found it. It's just I'm just trying to solve this equation for beta because there's a beta here and a beta here. So just go together. Yeah, that's what I said here. If you replace alpha by x bar minus beta z, you get this. Yeah, and then you solve from this equation, you can solve for beta. Yeah, together. All right, guys. Let me show you how to do this question 6. Your answer? Good. So you have x1
Now, I mean, there are many ways you can do this question. One way is to, you may remember. Okay, no, guys. You guys probably remember that I did an example on the exponential distribution some time ago, and do you remember the MLE that I got for lambda? What was it?
1 over x bar.
1 over x bar, guys. So this implies that the MLE for lambda 1 is 1 divided by the sample mean for the x's, right? You guys follow? And similarly, you're told that y1 to ym are IID exponential with parameter lambda 1, lambda 2. So by the same argument, the MLE for lambda 1 and times lambda 2 is 1 divided by y bar. Okay? Do you guys follow this? Yeah. Because this is, I think this is one of the examples I did when I started talking about MLEs. I think you should look back in the lecture notes, you will see that the MLE for the lambda parameter is 1 divided by the sample mean. Okay. Now call this equation 1, call this equation 2. Now if you divide equation 2 by equation 1, you will get lambda 1 hat equal to x bar divided by y bar. And lambda 2 hat is of course 1 divided by x bar.
Lambda 1 is 1 over x bar, and x2 is lambda 2 hat is just 1.
Oh, sorry, yeah, it's the other way around. Yeah. Thank you. Sorry, this should be lambda 2, guys. This should be lambda 1. Yeah, you're right. Thank you. Yeah. So lambda 2 hat is this, and lambda 1 hat is this, guys. I mean, this is the shorter way to do it. The longer way to do the same question is to write down the joint likelihood function of lambda 1 and lambda 2, and then take the log, and then take the partial derivatives and solve them, and you will get the same answer, guys. If you try it, you will get the same answer as this and this. If you do it that way. Yeah. Is that clear, guys, or not? I know you guys did the longer way, but you should get the same answer as this last. Yeah, you can use it. I think the question will tell you like whether you can use it or not. I think, yeah, you can. I think definitely you can use it. Yeah. Yeah, you can do it this way too, and you will get the same answer as this one. Yeah. But this is kind of long way to go. Yeah, you can, yeah. You should get the same answer, right? Yeah, just try to work it out. I think you should get the same answer. But you can argue that one of the carriers because it's high here, but it's high.
那你说这样都好的就是哦，除了这样就搞明白了。一般可能是就是刚才因为梦没有见到我就去不上。对。
为什么被这种直接用
All right, guys, can you do question 7, guys, now? Shh. Can you do question 7, please, now? This is question 7. You have x1 All right, now you should do the standard approach, guys. The standard approach would be this is the standard. The standard approach will give you this. This will give you this as the likelihood function. So the log likelihood will be n delta will be this one, and the derivative of the log likelihood will be n, and this makes no sense, guys. All right. So what this means is the standard approach does not work, right? So you have to try the, you know what to do if the standard approach doesn't work, all right? Is you try the indicator function approach, right? Which, so you write the likelihood function as do you see what I've done here, guys? I have put the condition that xi must be greater than or equal to delta, because if you look over here, guys, we have x greater than or equal to delta. That means every xi must be greater than or equal to delta, right? Yeah? So if you simplify this, you get this. Now let me ask you here, what would this simplify to, guys? Now remember, what would this I gave you some rules. If you look in the lecture notes, guys, you will see. If you look at the lecture notes, you will see that I gave you 3 rules for simplifying products of indicator functions. Now, what would this simplify to?
Every xi inside every
Huh?
Oh yeah.
This would simplify to the, yeah, you're right. The min the min of xi. Right now, the next thing to do, guys, is to your family. Now, how do you think the graph will look like? Just tell me, guys. You are the experts in calculus. You probably know more than me, guys. Now, how do you think you should graph this? You should draw a graph of this versus delta. Yeah. How do you think it will look like? How will it look like? Huh? It will be 0 on this side, yeah, because on this side your delta is greater than the min, right? Are you guys listening or what? On this side the delta is greater than the min. Now on this side, how would the graph look like? It will be an increasing function, right? Why is that? Because you have this n is a positive constant. N delta as a function of delta is an increasing function. Yeah. So your largest point is over here. All right. The largest point of the graph is over here, guys. I'm sure I've done this many times, guys. You should be bored by now. So your MLA for delta is the min of xi. All right, guys. And I have the attendance sheet back. There's one attendance sheet missing, guys. Why is it? You guys put the attendance sheet. You guys put the attendance sheet. Has anybody got the acronym shape? I can't find one. Where's the second
我们没有谈一下这个事情，谈一下，谈一下。
哦，这门课挺重要的。当然有几门都很关键的事，然后当然。
I gave you 3 rules for simplifying products of you need to use one of the rules. You just need to use one of the rules to simplify this to this. I gave you 3 rules for simplifying. I gave you 3 rules for simplifying functions and indicator functions. These 3. You just need to use one of them to simplify.
But use one of them to simplify all of this is okay.
Yeah, use one of them to simplify the products.
就是其实你看它那个入就是把后所有的连成下来就没有，一直接回是后面呀。
为什么是这样？
但是万一如果我因为如果你现在
不是这样。
如果你本来那个它没有冲的话，那它可能会催促。
不是，是这样，就是咱们回国的时候他很难受，那咱行李搁哪？咱回来的时候。
You understand what I'm saying? Just use one of the 3 rules to simplify the products of indicator
咱俩
functions.
吃这件事，没准这个是比咱俩
One of the rules, yeah. Which Yeah, you need to figure out. You need Yeah, you're right. Yeah, you just need to remember the 3 rules. Yeah, man, that's it. They're not really difficult to remember.
Yeah. When you simplify to this one, sigma is less than equal to minus x.
Yeah.
So why do you have to try?
Because
the biggest one should
no. You need to draw a picture because that picture will tell you where the likelihood is largest. Remember, the whole point of drawing a picture is.
You can see it from here.
Yeah, but the equations are sometimes they can be tricky. It's easier to see a picture than an equation. So right, you know what I'm saying. So it's easy. I think it's always a good idea to draw a picture before you can draw the conclusion where the largest point of the graph is. Yeah.
So it seems like when you need to solve this sort of question using an indicator function,
Yeah,
you still need to know how to draw all sorts of like pictures of
Yeah.
different distribution, like
Not picture.
exponential, uniform, or
Yeah, you just need to draw a picture of a function. That's it. So you just need to know how to draw a picture of a function.
But sometimes I really don't know how to draw a picture of like a beta function or wave.
No. Those functions will not come in the exam
So
or
it's,
the test.
it just will come like
It will be simple functions. Yeah, like this function, the one I did just
like
now.
EXP or uniform distribution.
Yeah.
Okay, I see it. Thank you so much.
Okay. All right, man. Pleasure.